Hello and welcome to this webinar on how connected vehicles and smart intersections can improve safety and traffic flow. I'm going to go ahead and get started as people join. And I first want to thank, recognize that this is a webinar that's being sponsored by the UC Institute of Transportation Studies. That's an organization that represents four institutes of transportation studies across the UC, including ITS, Institute of Transportation Studies at Davis, ITS Irvine, UCLA ITS, and Berkeley ITS. So thank you all. And we have really everyone represented here on the webinar. So it's really exciting to convey research across the UC. This is funding, many of the projects are funded through the Resilient and Innovative Mobility Initiative that we refer to as RIMI, which serves as a living laboratory, bringing together researchers, policymakers, public agencies to pursue research around a broad set of transportation topics. I want to make sure that we're familiar with how to use Zoom. I know at this point in time we all really are, but just to be sure, if you run into any technical issues, just let us know by typing a message into the chat box. The questions that are for speakers should go into the Q&A. So there's two different places that you can put in information and make sure that we do that in the right way so we can facilitate answers to those questions. And we may be answering questions in the Q&A feature live as well as chat. So our presenters today are Professor Jiaqi Ma with the Civil Environmental Engineering at UCLA, Junchen Zhang, a professor of Electrical and Computer Engineering at UC Davis, and Jonathan Lee, Chief Engineer and Project Manager at UC Berkeley ITS and Circles. So without further ado, I'd really like to get into their presentations. But first, I want to thank deeply participation from our Caltrans partners. Balwinder Tarlok is a branch chief at the Future Mobility Research Office, the Transportation Technology Research at Caltrans, and Sunny Gill, Chief of the Office of Ecosystem Delivery for Transformational Mobility, the Transformational Mobility Program at the Division of Traffic Operations at Caltrans. So those folks are going to provide some feedback on our presentations after all the presentations have commenced. So without further ado, we'll go ahead and get started, and I'll invite our first speaker to Professor Ma to share screen and go ahead and get started.
Sure, thank you very much, Molly. Okay, I guess you can see my screen now. Great. Okay, so let me just get started. So thank you for the opportunity to speak at the ITS webinar. So what I'm going to talk about today is the smart infrastructure. It's basically equipping our existing infrastructure with new technologies for safe traffic safety operations and connected automated vehicles. So I'll just get started. The background is that our existing transportation sensing system or sensory systems are the traditional detectors. They can get limited information for us. It's okay for conducting generic traffic congestion analysis. However, if you zoom into some local area, for example, at intersections, where we have so many different types of road users interacting with each other, particularly when you have pedestrians, very small size road users interacting with other like buses and motor vehicles, we need more detailed information, right? Traditionally, we do not get enough detailed information at, for example, a synchronized intersection with pedestrians, so we cannot really can fully consider these road users in our signal control and other traffic management strategies. So the proposal here is really that with these new technologies, why don't we include them here, right? We have seen how autonomous driving business has been developing so fast in the past years. Their technologies of detection, perception, tracking, and so on has been proven and pretty effective, and a lot of those technologies I think can be transformed, can be transferred right to our infrastructure. So our solution here, as part of this project, a few other this RIMI project and a couple of other related work, funded by Federal Highway and National Science Foundation and Caltrans, is to develop some solutions. We looked at concepts initially. What can we do, right? What are the technologies available out there? At a minimum, right? We have these deep learning AI technologies that's been developing so fast with unprecedented capabilities, particularly for computer vision, that it can see the world, detecting what is out there on our roadways. And there's a lot of edge computing and IoT capabilities like connected V2X, connected vehicles. So if we put them together, we will be able to transform the next gen our intersections and transform our traffic management. So we had targeted our audience with this work for state and city DOTs and technology developers to show them that these technologies exist, and we have developed prototypes, and this can benefit our road transportation pretty much as well. Last but not least, on this slide, you saw this V diagram. If you're familiar with systems engineering, what we have done in this work is not only developing algorithms, evaluating simulation, but we went one step further, actually many steps further, to develop prototype, deploy out in real world, getting real world data to prove this concept actually works. As I said, two advanced use cases. One is next generation safety and traffic analytics. We are using this multimodal sensors and our smart algorithms. These sensors may including LiDAR, radar, camera. We put them together, right? Each of them has their advantages and disadvantages, but we put them together, and we want to detect the details of the intersections, the details of merge area, and so on. So these two examples shown here, on the left is the picture is the LiDAR detectors can detect each individual vehicles and draw their bounding boxes, even we know their orientation, where they're driving, are they actually making lane changes in a minute, and so on. On the left side, obviously, the camera vision, we are tracking vehicles. For example, in this case, this vulnerable road users is crossing the roadways, and we'll see one vehicle is coming, and they're going to make a right turn. And we will be able to detect them, track them, predict the trajectories, and then we can identify there's potential conflicts, right? Spatial, temporally. So then we can deploy corresponding countermeasures, or, for example, issue warnings or changing traffic signals, better manage traffic, improve safety. So the other use cases is we connect automated vehicles where vehicles infrastructure can talk to each other, right? Because infrastructure, now the traditional automated vehicles, they based on their single vehicle sensors, all the line of sight issues our human drivers has. These vehicles, all autonomous vehicles also have. So there's they are also very much limited by their sensory systems. But if we have infrastructure, same thing. If we have infrastructure sensors, we can communicate that to the automated vehicles. Then they will be better perceiving all the surrounding environment and will perform much better and much safer and efficient maneuvers, right? They can plan safer and efficient maneuvers across intersections and other key locations or highway systems. So as at UCLA, what we did one step further, we not only developed all of the algorithms, right? I kind of listed a couple of papers on top of below the pictures you have seen. We've developed algorithms, but we want to put these algorithms on this real world intersection, and then to see how effective it is. And all of you know that once you put something real world, everything breaks, and then we have to figure out solutions to make it work again. So this is the UCLA Smart Intersection. We kind of over-equipped this intersection with multiple LiDAR, camera, radar, and V2X devices and edge compute devices. But this is really our living lab to show, to kind of explore different concepts, different sensors, different sensor combinations, and to see, how this technology will work, under what conditions this technology will work. Right, this is the kind of bird's eye view of intersection. This is kind of digital replica, digital twin of intersection, and this is a picture showing that how we mounted initially how we mounted these cameras and LiDAR sensors and the radar sensors at the intersection. One key question we were always asked is how expensive this deployment is. right? Is it possible for DOTs to actually deploy these technologies across the board, a lot of the intersections? We're looking at this different the prices. When you look at the prices, it's actually not that daunting, right? Because hardware camera is always cheap. You don't need like super nice cameras, so it's very reasonable price. The probably the most expensive, so are like radars. The probably most expensive is LiDAR. But LiDAR has different types, and LiDAR prices dropping as we see in the past couple of years. So we see that in the 5 years, maybe in 3 to 5 years, all these prices will drop significantly, and we see that below 8K to 10K at intersection, you'll be able to deploy such a solution. And this is very encouraging because it's no longer kind of lacks a solution, right? This is a solution that can benefit all the intersections, no matter where it is. This is our intersection pipeline, right? Our software is mostly, so we develop this hardware, we have all this interacting with different road users, connected vehicles, non-connected vehicles. We have connected our automated vehicles in our test bed too. But our key software solution is the box in the middle. We have automatically generate digital twins, so we can do a lot of simulation evaluation to suit what the best solution. And we have developed the object detection and tracking algorithm for all weather, all conditions. That really requires multimodal sensor fusion, right? Because camera is bad at nights, right? LiDARs and cameras as well are bad at during rain conditions. Radar is going to good at during diverse weather conditions. But when we fuse three together, extract different information from them, we'll be able to develop all weather, all condition solution. So that's the goal we have been always trying to do. And road user prediction, right? Because when we do safety analytics, traffic management, prediction is critical, and decision making, intersection control. And we are starting some projects to see how this information will be put into the traffic signal control for multimodal traffic signal controls, particularly considering road users. And we have continuous development in this intersection, which is very variable resources for us, and we continue doing verification and validation. And once we have a new algorithm, once we have a new system kind of prototyped, we'll test our intersections. And we are kind of also working with UCLA's technology development group to develop a product that is easily deployable for DOTs. But in the general, before I give you some visualization, in general, our UCLA smart intersection research is that can be captured in this diagram, right? We have a physical system, which is our smart intersection, smart test beds, but we have a lot of digital simulation that we have done continuously. We run a huge number of simulation. We have our own simulator open sourced to the community as well, just to be able to evaluate different scenarios. To understand what are the best traffic management, safety management scenarios for DOTs. We're developing a lot of challenging scenarios for the simulation, like weather conditions, like pedestrian crossing conditions, a lot of safety critical conditions, and so on. So we do evaluation, continuous evaluation. But I want to mention here is that another line of research we've been doing is because we have the sensors on the roadway anyway, we have deployed that solutions. We have developed offline, but we continue collecting data on our smart intersection, and it keeps updating our solutions, or gives us data updating our solutions, so we can have the best solutions for our intersection. So this is the digital map. I will some visualization for you in the next couple of slides. So this digital map we're using to conduct the detailed simulation. This is not just traditional traffic simulation we were definitely able to do, but also simulation. For example, the pedestrians are blocked in the line of sight, right? The vehicle's line of sight are blocked by a tree, and he cannot see the pedestrian. We can also simulate cases like this, so through that we can better evaluate the best technologies and detection technologies and tracking technologies for this kind of safety critical scenarios. This is an example of our multimodal sensor. This is a visualization of LiDAR and radar, right, from an infrastructure perspective and from a vehicle perspective. So again, we wanted multiple sensors together to be able to give all weather, all condition solution. And this is kind of fusing all the infrastructure and connected vehicles sensor together. That's our smart intersection. Just give you a sense how detailed the data we can get. These are very valuable resources no matter offline, offline for the research communities and for online operations also for DOT. So we just get, for example, we can see all these little dots here. These are all the pedestrians, right? We can see exactly where they are, where they're heading. This is the integration of tracking capabilities. Just give you a sense of how we can track individuals. We look at the trajectories, and we can use these trajectories to predict where they're going. Are there going to conflicts with other road users? And this is another view of sort of vehicle view as well. Like in this case, right? For example, this vehicle cannot see. Technically, this vehicle should not be able to see anything at this intersection, but is now able to see that because of this V2X information sharing. And this is actually a real-time, this is a video recorded in real time when we do this experiment, meaning that we can actually, through V2X, giving a lot of great information, much broader view of the intersection to the vehicles, so the vehicles can, the CAVs, for example, can plan better. So just to conclude, I think there's a lot of potential for smart infrastructure. We have explored a lot of the sensing and tracking prediction, even also localization capabilities. We have deployed applications connected automated vehicles. We have started working with traffic signal controllers for multimodal traffic signal control. A lot of great valuable information through smart infrastructure sensing, edge computing, V2X will benefit road safety and traffic management a lot in the future. I think this will be a good direction in the future for traffic management, for enhancing to revolutionizing our existing transportation infrastructure. These are our team members. They've done a lot of groundwork to get the intersection working, and also thank for Federal Highway Caltrans and RIMI to fund really the research. That's all my presentation. Thank you. Molly, back to you.
Thank you so much. And so I will turn over to our next presentation from Professor Junchen Zhang at UC Davis. And I wanted to take a moment to also introduce myself. I'm working closely with Junchen. I've realized in the beginning of our webinar, I didn't introduce myself. So I'm Molly Cohen-D'Agostino. I'm working with Junchen, directing this new program called the Mobility Science Automation and Inclusion Center here at UC Davis. I also serve as represent a portfolio of projects for the UC ITS and serve as policy lead for those projects in emerging tech and shared mobility. So yes, without further ado, we'll go ahead and present, excuse me, Professor Zhang. Thank you so much.
Yeah, thank you so much, Molly. So hi, good morning, everyone. It's great to be part of this webinar. I look forward to interacting with you and receiving your feedback. Oops. Yeah, so in this project on CAVs, a central question we are trying to understand, trying to answer is that what data to share, with whom to share, and how to share. So we've been working on theory, we work on algorithm design, also experimental studies. In this short presentation, I'm going to share with you some experimental results on how we can make use of V2V and V2X connectivity to improve safety of vehicle and also pedestrian cyclists. Okay. So the experiments are carried out on the simulator platform we are building here. We call it EI Drive. So this EI Drive is a hardware in a loop simulator, okay, for autonomous driving in mixed traffic. So why we consider mixed traffic? That's because automated vehicles and human-driven vehicles are going to coexist for many years to come. So initially, just a few automated vehicles, like from Waymo, from Cruise, and eventually, as time goes on, more and more automated vehicles will be put on the road. So it's very important for us to understand how to achieve, how to improve safety, how to achieve autonomy in mixed traffic environment. Okay, so we consider mixed traffic environment, and then the question, as I just said, is to understand what data to share and with whom to share and how to share. So let me use this video clip to illustrate. So in a mixed traffic environment, so we have human-driven vehicles labeled in red that you see in the top. Yeah, HV is human-driven vehicles, and automated vehicles are labeled in blue. You see AV on top, and then the data can be in a form of location, and it can be speed, it can be heading, and so on and so forth. So the question is with whom to share and how to share. Right? So whom may be neighboring vehicles, and this is subject to privacy protection and cybersecurity control. Okay, so we run the experiments in our simulator platform. Just a few more words on this platform we've been building over the past 2 years. So this is hardware in a loop simulator for autonomous driving. So it gives driving experience as if it were in real world. So you are welcome to visit us. I'll be happy to show you. Okay, you can experience it. So our platform provides both first-person view and also bird-eye view. And we have created a number of scenarios, driving environments beyond the ones offered in color. Okay, so let me use this short video clip to illustrate. So this is bird-eye view, and also we can change it to first-person view. Yeah. And we can change different driving conditions, different weather conditions, dark, rainy, foggy. We can also choose different types of vehicles. It can be Tesla or it can be a police car. Yeah, so on and so forth. Okay, so now come back to the central question, right? So why do we want share information, right? It's because oftentimes in driving, is not enough for individual vehicle just to make driving decisions based on local own observations. Okay, so in fact, we human beings, right? When we drive, actually we share our intention with other drivers too. We use turn signals, we use brake signals, so on and so forth. Okay, so information sharing is important. So let me use one example. The example without information sharing to illustrate the sort of like a potential danger. Okay, so in this example, say this vehicle, the white vehicle at the bottom actually is the Eagle vehicle, and the next to it is a fire truck. So it's blocked. The Eagle vehicle is blocked by the fire truck. So there's another vehicle coming into the intersection. This gray vehicle coming into the intersection. And this window here is we call it a safety mind map. So let me use this to share with the view. So the gray vehicle coming to the intersection, and then the Eagle vehicle sees it only after it gets here. So it's too late. So if before the Eagle vehicle sees the gray vehicle, it would enter the intersection, then there might be a collision. So this is no good. Okay. So, but there's another vehicle you see here, the blue vehicle across the street. You can see this vehicle. If we can use VTV connectivity to share information, this would improve safety. Okay. So, all right. So the question is, how do we do information sharing? So in this example, in this experiment, we use the V2V connectivity, V2V communication to do information sharing. Now, the next question is what data to share, right? So there are different approaches. You can share information about your nearby objects, your intention, or you can, do better by sharing sort of the so-called latent representation, latent embedding. Okay. So let me elaborate a little bit on this. Okay. So there are different options what data to share. One option is to share the sensory data coming from cameras, from LiDAR, right? So if you look at the details, right, each camera observation, each frame is about 150 kilobytes in size. So if we have for 3 cameras, it amounts to about 450 kilobytes. When the LiDAR is about 600 kilobytes. So for one frame, if we want to share data from 3 cameras and 1 LiDAR, it's about a 1.05 megabytes. The times 8 is about 8 megabytes. This per frame. So typically it's about 20 frames per second. So the corresponding bandwidth requirement would be about 200 MBs per second. This is for one vehicle. This is a lot, very, very demanding. Okay. The second option is to share information, so-called safety mind map. So this safety mind map is a high score notion, a concept in the leaderboard in color. Okay. So each mind map is about a size of about 20 meter by 20 meter. It contains data on occupancy probability, velocity, heading, bounding box, and so on and so forth. So the corresponding bandwidth requirement is about 11 kilobytes. So compared to sharing the sensory data, this is much, much less in terms of bandwidth requirement, and can meet real-time the latency requirement. And we can even do better. We can share latent embedding, latent representation in word model, such as is used in Tesla Foundation model. Okay, so the different options. Okay, so in the next example, let me show you how we, in our experiment, when the information sharing between the Eagle vehicle and the blue vehicle across the street. So, and again, here, this window here, you see this looks kind of black, but is a safety mind map. Yeah, so you see, this Eagle vehicle, when the V2V information sharing, it has an enlarged mind map. So you can see more clear of the driving environment of the intersection in this case, and you would improve safety. Safety for both for the vehicle and also for potential pedestrian and cyclists. Okay, let me say a few more words about the safety mind map. So this safety mind map, as I said, is a high scoring notion in the leaderboard of color funded by DOT. So it's built upon multimodal sensing. It basically is a 2D grade reconstruction, as shown in this blue picture here. So it takes input from camera sensors, from LiDAR. It's a map. It contains information about all objects near the Eagle vehicle, including vehicles, pedestrians, cyclists. So you would improve safety for all of these objects. So, okay. So with that, the map would basically, it would give us occupancy probability at each cell. For instance, if we look at this map, right? So there are 4 objects and 1 pedestrian. They are all mapped to this, the 3D actually here in the safety is is the corresponding occupancy probability here. Okay, it's higher would be higher probability and lower, and that's with a small probability, right? So that's the safety mind map. And as I said, it's built upon multimodal sensing from camera, from other sensors. Okay. Okay. So with that, let me move to the next experiment to illustrate how can we use V2X connectivity to carry out infrastructure-aided sensing and perception. Okay. So again, I'm going to illustrate the contrast 2 scenarios. One scenario is without using V2X connectivity. Each vehicle, Eagle vehicle, just by itself. And then second scenario is with the help from infrastructure, as Judge just presented, right? When the infrastructure has rich data, sensory data, with the help from infrastructure data, each Eagle vehicle can do a much better job, can get a much clear picture of the driving environment. So in this experiment, you see at the top, they are the red ones. Okay, they are infrastructure devices, so RSUs. They are red, so they are turned off. So vehicles coming into this intersection, say, without coordination, without help from infrastructure, an accident would happen in this scenario. If we move on to the next experiment, with the help from infrastructure, the RSUs are turned on, they communicate with the vehicles, about the driving conditions, driving environment, and then it would improve safety and also improve traffic throughput. Okay, so let me conclude. So a central question in this project is to understand, first to understand what data to share. We can talk about different options, like, can be raw sensory data, can be safety mind map data from in safety mind map, and what can be, we can even do better using latent representation in water model. This is something we are continuously working on. So, and then with whom to share, with the living vehicles and what else, right? With whom to share and how to share. We talk about different options, V2V, V2X, V2I. So one data sharing has to be subject to privacy protection and cybersecurity control. This is something we are also working on as well. So clearly this requires understanding from both technology perspective and also public policy design perspective. Of course, at the different scales, city level, county level, state level, because Caltrans can play a very essential role here and the federal agency. So I'll stop here and take any questions you may have.
Thank you so much. This is so fascinating. I think in the interest of time, we will move to our next speaker and then we'll take some questions after that. But thank you so much, Professor Zhang.
Thank you. Let me stop sharing. Okay.
Great. And we'll transition to our final presentation from Jonathan Lee at UC Berkeley.
All right. Thank you very much. Hi, my name is Johnny Lee. I'm the chief engineer and project manager for the Circles Consortium, which is comprised of the research institutions and industry and government partners that you see below. Today, I'll be talking about the Mega Vendor Test, which is an experiment that we ran in live traffic last November, and the technology that we built for it. So the problem that we're trying to solve is basically traffic. These are some examples of well-known phenomena that happen in traffic, and I'm sure we've all experienced the frustration of sitting in these different phenomena. These things, stop and go waves in particular, create a lot of problems that go beyond just frustration. So there's fuel inefficiency, there's greenhouse gases, there's safety incidents, there's a whole number of things. And this is essentially what we wanted to tackle. I'm going to show a brief video and I'll see you on the other side of it. I'm sure many people have experienced stop and go wave. You need to slow down all of a sudden, and then once the traffic clears out and you start moving, you didn't see anything that was the cause of it. Usually this is because a vehicle taps on its brakes, and that creates a chain reaction that goes to the next car and the next car and the next car.
And that's precisely what the technology tries to fix. Self-driving vehicle technology was born at Berkeley, and what we're doing this time is we're enabling collaborative self-driving. So you put many vehicles together and you teach them how to operate in coordination to improve the overall traffic.
Circles is a project that we are deploying 100 vehicles with adaptive cruise control. We modify the adaptive cruise control just a little bit, and we design that to make traffic better for everyone. 100 vehicles, all running modified adaptive cruise control, 40 staff, 120 drivers that are here executing the experiment. It's really exciting to see things get out of the lab and into the real world where we think we can make a real difference.
There's one of ours. Okay, great, good.
We showed that it was possible to dampen these traffic waves that come just because of increased congestion by making small changes to the speed of 1 out of maybe every 20 vehicles. And by having that single vehicle drive differently, all the vehicles behind would drive slightly differently, and that saved a tremendous amount of fuel. So what we're witnessing today is the deployment of this idea at a grand scale.
So I'll cut the video short there in the interest of time, but what was alluded to in the video is essentially the solution we're looking at is this collaborative environment. So connected and automated vehicles really opens the door to this collaboration. What we're talking about here is you could think of it as Google Maps, but kind of on steroids. So Google Maps, your phone pings to Google and tells Google that at this location, this phone is traveling at this speed. And that information is aggregated in the cloud to tell all the users to say, this part of the road has traffic or this part does not have traffic. What we're able to do with automated vehicles now is say, if you were to share that information, then we could know very precisely what is the speed at every part of the highway, and that information can be used intelligently to determine sort of an optimal way to drive, and that would optimize the traffic flow for everyone and essentially address all of the issues that arose from the previous slide. This is the technology that we built, depicted very, very simplistically. Essentially, there's two levels. There's the cloud, and then there's the connected car. On the cloud side, we basically aggregate the traffic data that's coming in from the cars and other data sources, and we compute what I call a globally optimal speed field. And that's basically just a fancy way of saying this is the ideal speed that we think that everyone should be driving at every position on the highway. Obviously, you can't expect everyone to drive at that speed, even if they wanted to, because a car might be cutting in, there might be merges, there might be a slow driver for whatever reason. And so on the vehicle side, that car, an individual car, will get that information from the cloud, but also have information from its own sensors, and it knows that okay, I'm driving behind a very slow car, or I was just cut off, or whatever, and it will produce its own locally optimal speed. So something that is optimal for itself, taking into consideration things like social acceptability. So you don't want to be driving 20 miles per hour slower than the car in front of you. People will be very upset with you. So moving forward, we basically want to understand what is the barrier to getting this technology out into the wild. Technologically, it's relatively simple, right? You just need to be able to provide this data feed, which we could provide, someone like Google Maps could provide. This is relatively simple, and then you just need a 4G LTE connection on the car, which a lot of cars nowadays do already have. Those are simple. The more challenging aspect of it is, how do you incentivize people to want to do this? So as a commuter, I'm selfish, right? I want to get to my destination fast. I don't really care how my driving impacts the car 20 cars behind me, or how it impacts greenhouse gas emissions, right? The OEMs are the same. They're also selfish. They want to sell more cars. They don't really care about what is the impact of traffic and congestion and climate change to an extent. And really, why do they want to share data with the other OEM company? So this is a challenge, and at some point, we believe that probably government needs to step in and say, here's a new policy that will align the incentives of all the multiple players involved. But we haven't really gotten to that point yet. This is my last slide. So just moving forward, what we want to do in the next year or 2 years or so is to deploy pilots in multiple regions within the US, and we're not talking about 100 drivers now. We're talking about daily commuters, so maybe 1,000, 2,000 drivers, and really understand what are their pain points. Does this technology even help them? Is it something that they would be willing to pay for, and how much? And just understanding, what are the factors that drive this? How do you get this technology out there? And that will also help inform the OEMs that if they want to get involved, these are the factors. And so I'll leave it at that. If any of my talk has sparked any kind of ideas or interest or whatever in your head, please don't hesitate to reach me by email. And thank you very much.
Thank you so much, Johnny. And you certainly have sparked ideas for me. And I am sure that our participants also have questions. I don't see any Q&A in the chat, but this would be a good time to ask questions of our speakers. I'm going to turn it over to our guest respondents from Caltrans. First, Balwinder Tarlok will provide some initial responses to the presentations and convey some of the priorities from his office on these topics.
Thank you, Molly. First of all, all the three presentations are so great. It just gets us to the ground reality of the interesting times we are living in. So I'll get back to the presentations now, especially Johnny, on your presentation, how you mentioned about the selfishness, how the drivers are selfish, OEMs are selfish. So one thing which I think from Caltrans perspective, we should not lose out is on the equity and inclusion perspective, and that's very, very important for us. What happens is in this race of trying to get the automation, we don't want to encourage just a single owned vehicle promoting that, because that automatically is going to not bode very well for the other users of the state highway system, vis-a-vis shared mode. If you take at that, recently we've seen a lot of robots also coming up. So multimodality would be a key, and the inclusion piece of it and equity, those are two very important things. With that, I'll move on to the first presentation that was provided by Professor Jakima. I think he covered the multimodal aspects of it very well. But what I found missing in that was actually he had every slide had cars to be showing. Instead of, he did come up with a lot of multimodal sensors, a lot of vulnerable road users, and great actions. But if we could include these in the slides to show that these are multimodal, by that I mean is the other modes. We have got freight, we have got transit, we've got pedestrians, and like I just mentioned about robots also coming into the field. So that's from my perspective from the Department of Transportation, because we want to have a futuristic infrastructure which is equitable to everybody. So I'll stop there, and it's really interesting and heartening to see that the great work which has been done here by everybody. And as regards to Professor Jinshan, I think that slide which gave us the cost factor of it in terms of 2,300, the cost really, infrastructure is not the cost, but say if we leave certain people behind, that's the bigger cost we need to be worried about. In all this enthusiasm, we don't want to have those people left behind. So if we could include that cost also, even if we don't have a cost at this time, even if you put that over there, that this is what it'll take, and that will get folks at Caltrans, at local agency, to think more about it. So I'll stop there. So thank you again. Great presentations, all three. Really enjoyed it. So I'll stop there, and back to you, Molly. Thank you.
And thank you for that. I think emphasizing multimodalism and equity is an important theme in this work as well. So thank you for that. Sunny, do you have any other feedback for our presenters and around this topic?
Yes, thank you, Molly. Thanks for inviting us, and thanks for a very important presentation from all three professors. I really appreciate the theme you started with: smart infrastructure at the intersection, using an equipment at the intersection, and then going for a automated vehicle, and finally doing a use case in the freeway using all these automated vehicles and technology in one package. Although Balwinder had mentioned equity cost and social cost as a part of the technology, but I'm still interested in the life cycle cost of any of these technologies being deployed at our infrastructure. So anytime I have a project or a project scope and a project idea, previously, and 10 years ago, everybody was deploying new things and they install it. they will forget about it after 1 year once the warranty goes away, and then they will start degrading and maintenance was not a priority. But since then, the department has really focused on what's the total life cycle cost of owning any device or technology, which will factor in the operation cost after the first year and the maintenance cost for the life cycle or the time when the device is operational on the freeway. So I will really appreciate going forward if any of these researchers and professors and universities at least have a paragraph in the end of the report about life cycle cost of this research project, so that I can take that number to my management and say, okay, yeah, it's going to cost $10,000 to upgrade the infrastructure, but I still need $50,000 to program my maintenance cost and my operational cost for next 5 years. And this is the life cycle for 5 year or 10 year. What is the cycle of this technology? And the second point I would like to make, in all these new technologies and new detectors and sensors, which we are all testing and making a tremendous progress, is the interoperability of these devices with each other. Yes, you picked a LiDAR from one manufacturer, camera from another, but as for a Caltrans DOT perspective, we have to be very open source and make sure that all companies have equal options to deploy their products. So typically we will rely on something called a performance spec out of a research, which I can use to be my minimum criteria I want to deploy. So if I have a LiDAR who has 5 GB memory or how many point clouds they can process, if Professor Ma can tell me that, hey, Sunny, you need a LiDAR with 3,000, 100,000 points being processed, that's the threshold I will ask for all the manufacturers, and then XYZ company can meet that. So those are the couple of points I will present in relation to deployment of these technologies. Thank you for all.
Yeah, well, Sunny, thank you for those thoughts. And actually, the question I was going to pose to the presenters was on interoperability. So thank you for really starting us off on that conversation. So I want to sort of pose this issue of interoperability. I know this is something that comes up quite a bit. Will vehicles from New York be able to interact with smart intersections in LA? Will what types of standards, what types of policy are necessary to ensure that these types of devices, and I understand that we're talking about a number of different sets of devices across these projects, can be interoperable within California and among our, across the country. And I guess this is a question. How about I don't know who would like to start it off, but I'm gonna tap Jachi to address this question, because I know you've also done some work with NHTSA on this issue. So
yeah, I think the interoperability is a critical question. It's a part of the process of V&V, verification and validation. Every time you develop technology, absolutely, when you in your design, you have to have the interoperability as part of the design. But when you develop it, deploy it, and obviously the whole V&V verification and validation process got to include that big piece, big component. Good example. I think Sunny Gill just mentioned that, right? If you have a LiDAR point cloud processing, what is the need for that? And exactly what we are trying to do, we kind of over-equip in the section. We try to play with different sensor combinations, trying to understand that requirement. So it's almost like under the systems engineering V diagram, there's a part of is the system requirements. A lot of places we just deploy one-off solutions, but what we are trying to do is to understand that requirement. To do this, you need this capability. Now, this capability includes the sensor capability, but also processing capability, connecting to water, and how it can be connected to your traffic signal controllers. There's so many questions that we need to answer. I think we are. I will not be able to answer all the questions today. We have actually going to do some projects as well to look at the overall sensors and their connections with each other, how they can supplement each other. Actually, it's one of the upcoming projects. But it's definitely a critical step, ongoing work that we're doing now. Yeah.
absolutely. Thank you. So I'll pivot over to Professor Zhang to speak to this question of interoperability.
Yeah, thank you for posing this important question. I think both of you, Sanya and Molly, you already provided partial answers, right? So standards. So we need to have, would be great if we have a uniform standards in terms of like connectivity, communication standards, in terms of computing standards, in terms of data format. Say if one vehicle shares data with another, with the infrastructure, for instance, or with another vehicle in nearby, with data sharing, but the other vehicle cannot decode it, cannot make sense out of it. It doesn't, it's not of no use, right? So it's very, very challenging. It's impossible to have uniformization across different OEMs, across different equipment companies. So it's there's no simple answer. It's very challenging. I think we have to, work together. OEMs, city, county, state, federal, right? Try to come up with solutions. Together, join force. There's no simple answer.
Absolutely. Wouldn't it be nice if it was simple? But it is
Uniform,
complex.
There's no way to get a uniformity.
Absolutely. So Johnny, can you speak to this issue? I mean, you worked in another state. The project, the Mega Vander test, was done in Tennessee. I'm sure interoperability was a big discussion point amongst your.
Yeah, so what we deployed in Tennessee, we used a third-party data source called INRIX that maybe people are familiar with. And INRIX is, to my knowledge, is worldwide. So that really opens the door to having it, be in any geography. And I think what Professor Zhang just kind of touched on is a really key point, which is how do you get the different OEMs to use sort of the same standard? And fortunately, we were able to get kind of under the hood and work with different OEMs. So we worked with Toyotas and Nissans and GM and so I think it really requires that there is a third party that is involved that can sort of set that standard and the OEMs work with, as opposed to a single OEM being sort of a central server and then other OEMs playing ball with that. I find it hard to imagine a world where, Toyota is willing to use Nissan's standard and send all their data over to Nissan, right? So I think it really requires that third party, and this is something that we're working on going into the next year or two of our work.
Yeah, and if you don't mind expanding, Johnny, on the question that was asked about a potential deployment in San Diego.
Yeah, so like I said, we don't have anything concrete yet. We have talked to a couple of different areas. The map that I showed included San Diego because we did have a conversation with Sandag about a potential deployment. We also were talking to some folks over in Austin. I think the main barrier there is even if we had the technology up and running that could be deployed in all these different geographies, it's really, at this point, it's a recruitment problem. How do you find the 1,000 or 2,000 drivers that will want to participate in this, and are their cars even suitable for the technology, right? If it's a Toyota Corolla from the year 2000, right? Like it probably won't work. So we haven't really started to tackle that problem yet. And I think the first place we want to tackle that is in the Bay Area. And once we kind of have one location under our belt that we know how to recruit such large numbers, then we will start to look elsewhere.
Just tackling traffic in the Bay Area, no big deal. Well, we encourage you to do that. And obviously there's, there's a lot of work to be done in this space. I wanted to, it doesn't look like we have any additional questions for the panelist. So I wanted to just provide you an opportunity to just, if anyone has any closing thoughts or thoughts that weren't addressed today. Otherwise, I have some closing points. Okay. All right, well, I wanted to say that these projects, this was a teaser, right? We had 3 brilliant professors, 2 guest respondents. This is far too many topics to cover in 1 hour. So we really see this webinar as a teaser. There is so much more here. We really invite everyone that participated today to reach out to me, to reach out to our speakers, to set up additional questions. I'll put my contact information in the chat. I really want to serve as an intermediary between you all and these experts, so we can really be fostering a productive dialogue between our presenters and our audience. I'm going to I just want to thank the sponsor of this event, the University of California, UC ITS. Again, there's a lot of really amazing work being done at the UC ITS, and this is just a sliver of it. So we are really happy that we could present this work to you, and we serve as this transportation research arm of the state. We will be sending out a poll which would allow people to provide feedback on today's session. And we really do encourage you all to go ahead and provide us that feedback. It really does inform our efforts in improving these webinars and making sure that they are, a good use of your time. And that is our goal. So thank you all to everyone who participated today. There's the slides, and of course the recordings will be available on today's webinar event webpage, which you can find at the link provided in the chat. So thank you all so much. We really appreciate you joining our this event and future webinars around UC ITS research. Thanks again, everyone, for joining, and I'll conclude the webinar this time.
Thank you.
Thank you,
Thank
Molly.
you, Molly. Thank you, Molly. Thanks.
Thank
everybody.
you, everyone. Yeah, thank you.